All right, so let's see how we can determine the behavior of each of these sequences. We're going to try to determine whether each one of these converges or diverges. And if it converges, we're going to find out the value to which it converges. If it diverges, we are going to say why. So on example 2a here, we've got the sequence 1/2, 2/3, 3/4, 4/5, etc. And the nth term is in the form n over n plus 1. So we ask the question, what happens to the limit as n approaches infinity of that nth term? What does that nth term approach? And we know that that equals 1. Therefore, the sequence converges to 1. Okay, that's the looking at the degree, right? The degree of 1 on the top, the degree of 1 on the bottom. The same degree means we look at the coefficients, the coefficient of 1 versus 1. So 1 over 1 equals 1. You can L'Hopital this one, but that might be a bit overkill, but it would work. All right, this next one, we've got 1/2, 1/8, 1/16, etc. The generic term, the nth term is 1 over 2 to the n. So we ask the question, what happens when we take the limit as n approaches infinity of 1 over 2 to the n? And we know that 2 to the n goes to infinity, so this is 1 over infinity, which equals 0. Therefore, the sequence converges to 0. And that's all we've got to do. Now this one's a bit strange. We've got -1 raised to the n as part of our nth term. So let's make sure we understand that. We're going to see that so often that it's going to become second nature to you. But for now, when in doubt, expand it out. So I'm going to look at n equals 1, n equals 2, n equals 3, n equals 4, etc. And if n equals 1, then I'm going to have 3 plus -1 raised to the 1. Well, that's equal to -1, so plus a -1. All right, when n equals 2, then I have -1 to the second power, which is actually +1. So we have 3 plus 1. All right, and then when we let n equal 3, we have an odd number of factors of -1, so that's odd number of negatives means we keep it negative. And then we're back to 3 minus 1. And it doesn't take too long to figure out that this is just going to be a +1, and it's going to keep on flipping back and forth between a +1 and a -1. And we are going to be adding each one of those to 3, alternatingly, in an alternating sort of fashion. So 3 minus 1, 3 plus 1, 3 minus 1, 3 plus 1. This sequence of 2, 4, 2, 4 does not converge. This diverges by oscillation. Remember that limits exist when the values approach a single value. The terms approach a single value, and 2 and 4 are not the same value, so this is an oscillating problem. All right, cool. All right, so let's look at this next one, part 2D. We'll take the limit as n approaches infinity of n over 1 minus 2n. Well, the degree on the top is 1, the degree on the bottom is 1, so we're going to look at the coefficients of 1 and -2, and we get -1/2. Therefore, the sequence converges to -1/2. All right, let's take a look at something a little bit more interesting. All right, we've got this one right here. We've got natural log of n on the top. We've got n on the bottom. We ask the question, what happens when n approaches infinity of this natural log of n over n? And this is for certain a L'Hopital candidate. We can use L'Hopital's rule. But here's something else we can consider. Because we're going to be seeing a number of these functions. We want to kind of save ourselves some headache. We're going to start learning the hierarchy of infinities. So let's spend a moment talking about the hierarchy of infinities. Okay, so I'm going to look at all of these different functions. For example, natural log of n. As n grows to infinity, natural log of n goes to infinity. If I look at n raised to the a, this also goes to infinity for positive values of a, as long as a is positive, right? If a is 1/2, right, let's look at a subset of this. For example, we could have n raised to the 1/2, we could have n raised to the 1, we could have n raised to the 2. And in fact, the bigger a is, the faster this thing is going to grow. So the bigger the infinity. But, and that's kind of the goal here, is to try to create an order of infinities. The next step on the list would be exponential. We've got not always e, often it's e, but it's any base a raised to the n. Those will also go to infinity as n goes to infinity, provided that a is greater than 1. If a is less than 1, we've got a decay problem, and this thing will approach 0. So that wouldn't fit in this hierarchy of infinities. Okay? But the bigger a is, the faster it's going to grow, right? 1.1 to the n is going to be an exponential growth problem, but it won't grow nearly as fast as 17 raised to the n. So the bigger the base, the faster it grows. All right, next up on the list is n factorial. N factorial also goes to infinity, and it goes to infinity even faster than the exponentials. Okay, and then the last one on this list is going to be n raised to the n. This one also goes to infinity, and it goes to infinity even faster than n factorial. So all of these are infinite as n goes to infinity, but not all infinities are created equal. Natural log of n is the smallest infinity we have, and since n raised to the a, in this case n raised to the 1, is a bigger infinity and it's on the bottom, we know that this is going to converge to 0. Therefore, the sequence converges to 0. Now, you might say, L'Hopital's rule is a lot faster than listing out all of these, but your task is to memorize this hierarchy of infinities so that you can recognize, oh, small over large, that's got to equal 0. If it was flipped, if it was small over large, I mean large over small, then the opposite would be true, and we'd have something that diverges to infinity. So if you don't remember the hierarchy of infinities, you can use L'Hopital's rule, but good luck trying to take the derivatives of these, especially the n factorial. So I would recommend memorizing this hierarchy of infinities. This is from small infinities all the way to large infinities. Okay, and let's do one more example at least. Let's take a look at this. One thing we might want to remember is that the factorial function can be defined recursively. N plus 2 factorial is the same thing as n plus 2 times n plus 1 factorial. But n plus 1 factorial is the same thing as n plus 1 times n factorial. And if we understand that recursive nature, then we can say, well, wait a second. There's a factor of n factorial on the top and on the bottom of this fraction. So this fraction reduces to 1 over n plus 2 times n plus 1. And that is clearly, that is clearly going to head towards 0 as n goes to infinity, because we've got 1 over infinity times infinity, and the bigger the denominator gets, the smaller the fraction gets. Therefore, the sequence converges to 0. All right, I think we're kind of on a roll here. I think we can maybe get a few more of these squeezed into this video. We just did an n factorial problem. Let's do another n factorial problem. This time we've got 2n factorial on the top, but be careful, this is not the same thing as 2n parentheses factorial. That's wrong, so actually we would much prefer it not to be that anyway, because that's harder. So remember, this is order of operations. The factorial only applies to the n. So remember that n factorial is n times n minus 1 factorial. And I'll stop there because I'll notice that my denominator has an n minus 1 factorial as well. So n minus 1 factorials are gone, like the noble gas argon, and this fraction reduces down to 2n. But that's easy because the limit as n approaches infinity of 2n is infinite. Therefore, the sequence diverges to infinity. Okay? So with factorials, we like to see that canceling out going on. All right? Let's take a look at this one. Maybe we'll zoom in a bit to give us a little bit more space. All right, so when in doubt, expand it out, especially when we see this plus a negative 1 raised to the n. That's a little bit odd. So I'm going to make this one a vertical. My n values of 1 and 2 and 3 and 4. All right, So when n equals 1, we get 1 minus 1, which is 0, over n, which is 1. When n equals 2, we get 2 plus 1, which is 3, over 2. When n equals 3, we get 3 minus 1, which is 2, over 3. And when n equals 4, we get 4 plus 1, or 5, over 4. Now, it may not be immediately obvious what this pattern is, so it might help to extend this out a little bit more. And it also might help to notice that we actually have two sequences. One sequence when n equals odd values, and one sequence when n equals even values, right? When n equals odd values, we're subtracting 1. So 1 minus 1 is 0, 3 minus 1 is 2, 5 minus 1 is 4, and then the denominator is just whatever n is. And then for the even ones, we're adding. So 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7. All right? So we can ask the question, what happens to each one of these sequences? So we go from 0 to 2/3 to 4/5 to 6/7 to 8/9 to 10/11. Those are values that are getting closer and closer and closer to 1. And then we look at, from below, right? And then we look at these values of 3 over 2, 5 over 4, 7 over 6, 9 over 8, 11 over 10. These are values that are also getting closer and closer to 1, but from above. So this is definitely alternating, like the oscillating sequence that we saw over here on part C, small, big, but unlike this one, where the small and the big are just stuck or perhaps approaching two different values, on this problem, these are alternating back and forth, but getting closer and closer and closer to the same value. So because the limit of all of these is equal to 1, we would say that the limit as n approaches infinity of the nth term is equal to 1. Okay, graphically speaking, we would kind of bounce back and forth. Too big, too small, too big, too small, too big, too small. But we're getting closer and closer and closer to that value of 1. Okay, so therefore the sequence
Mr. Pomerantz
converges to 1.